We're going to start chapter 7, which is starting kind of a unit over similarity in trigonometry, okay, which is going to get us to the point of being able to use like sine, cosine, and tangent on our calculator, and really understanding what that stuff means to us. The thing I'm showing you right now, though, is kind of how our end of course exam breaks down in regards to the content of it, the types of questions they're going to ask. And really, the only thing I want you guys to kind of pay attention to here is these. So all these like codes in between, in the middle, are standards that are referenced throughout these concepts. But what I want you guys to look at is congruence and proof. Okay, so that's the category. So that's talking about showing triangles congruent, working with triangles congruent. And there might be algebraic problems that are involved in here, and there might be proofs that are involved in here. But it's essentially everything we've talked about so far that is going to make up anywhere between 33 to 39% of your test. Okay, so a little bit under half of your test will be congruence and proof stuff. All right. What we're going to start today is this stuff. Similarity in trigonometry, okay, which is talking about ratios and proportions and stuff like that. And that's going to make up a quarter to a third of your test. Okay. And then the remaining part of the test, which is, again, can ultimately be, if we do like the addition of these, it could be upwards of like a third of your test to a half of your test. Is going to involve circles and probability. Okay, so right now, what we're going to focus on is getting a good understanding of this category of ideas. Okay. And this will set you up to be successful in a trigonometry course as well. You've already seen some of the stuff last year. I know you guys did sine, cosine, tangent a little bit with some algebra problems. But I want to show you, explain to you what that stuff means, where it comes from, what those buttons are doing on our calculator, and that kind of stuff. Okay. But in order to get there, we need to revisit some stuff about ratios and proportions that maybe you've seen in other classes. There's some notation stuff that we'll talk about. I think the number one error people have with ratios is units. So we'll talk about how we can adjust units and make sure we can manipulate those the way we need to. But in getting to that stuff, we need to talk about what a ratio is, first of all. A ratio of one number to another is the quotient when the first number is divided by the second. Okay? So what we're going to talk about here is that order matters when we talk about ratios. Okay? If I say that this wouldn't be true, but let's say I'm twice as old as you. Okay, I told you my stuff first, my information, and then your information, right? So it's a 2-to-1 ratio from me to you. Okay, if I say you are 1/2 the age of me, that's a different comparison. Does that make sense? Because now your information came first, my information came second. Okay, so when we talk about a ratio, order is important. Okay, that's not a terrible definition. Tells us everything we need. I like to say that a ratio is the comparison of two numbers through division, which is exactly what that says. It's just easier for me to say. So you might hear me say comparison of two numbers through division. All I'm saying is ratio. Okay. We've got a couple different ways of denoting a ratio or writing down that we are dealing with the ratios. The first one is not all that conducive to actually doing math with it and doing calculations, but it's writing it this way. 3 to 9. We actually use the word 2 in between. Sometimes we will elaborate on that and we'll say 3 compared to 9. But that then allows us, and I don't have the other one written here, to rewrite it this way. 3, you guys remember seeing it 3:9 in maybe the 7th and 8th grade or whatever? Okay. That's another one. We still read that 3 to 9 or 3 compared to 9. But the one that makes it most conducive to actually doing some algebra here is to actually write it as a quotient, write it as a fraction, okay? That is, all these words hopefully start to make sense on why we have our rational numbers. You remember our rational numbers being the numbers that can be written as A over B, as a fraction, okay, where B cannot be 0. 3 over 9 is one of those, okay? So it's a ratio. The root word for rational is ratio, okay? So we got 3 to 9. Still can read it 3, 9, 3 compared to 9, 3 divided by 9 now. But when we make comparisons, we like to do that in lowest terms. It makes sense most of the time to do it in lowest terms. So we like to rewrite it as 1 to 3, okay? It doesn't make a whole lot of sense to say, I am 4 times older than twice your age. Doesn't make a whole lot of sense, right? It'd be better to say I'm twice your age than 4 times twice your age. Does that make sense? So that's why we like to reduce things. One thing you got to be alert of is that you're not going to divide by 0. You cannot divide by 0. That's one of our main algebraic principles. I don't think there's ever a situation that, through the problems that we're going to get, that would be an issue. You just got to be careful, okay? Because Math Excel is going to ask this. They're going to want you to make sure you write things in simplest form, okay? There will be times where doing the algebra will be best in simple form, but there'll be times where it's best unsimplified, okay? We might do the algebra with the unsimplified fraction, but then when we answer questions in Math Excel, we want to make sure that we're abiding by the rules, and they say if it needs simplified, simplify it. That'll be when we talk about like scale factors and stuff like that for different shapes, similar shapes later on. It might be easier to use like a 4 to 2 ratio to actually find values of maybe an unknown distance. But then when I'm typing things into my Math Excel and they ask me what is the scale factor, I don't write 4 to 2, I write 2 to 1. Does that make sense? But 4 to 2 was better in my algebra, my setup for that question. Here's just an example. So when we talk about ratios, and this is just a notation thing, maybe a vocabulary type thing. When it's a ratio, it's a number compared to a number. There are no units. Okay? Kind of explain what I mean by that here in a minute. Let's say that all of these distances here are in, let's just say, meters. Okay, so I got 20 meters there, and I got 6 R meters here. Okay, where I don't know what R is, but I don't really care. When I want to compare the ratio of AC to BD, okay, AC to BD as a fraction would be that, right? Okay, I'm going to write that as 6R meters over 20 meters. Now, just like common factors, what happens with those meters? If one's on top, one's on the bottom, they disappear. Does that make sense? Just like there's a 2 here, and there's a 2 in there, they're going to cancel out. So I'm left with 3R over 10. There are no units there when we talk about a ratio. That makes sense? Okay. And that's for the mere fact that the units canceled, much like common factors canceled. If I were dealing with, like, let's say that 20 was in centimeters and 6R was in meters, I would have to adjust one of those. Okay? I don't want to take meters divided by centimeters or centimeters divided by meters. There's going to be issue with that. Okay? Ratio, we don't have units with it. Okay? The next one, find the ratio of C to D. Okay? So 80 degrees would be C, right? D would be 40 degrees. What's that reduce to? Units cancel, right? 2 to 1. And understand this, it's telling me how these two things compare. How much bigger one of them is compared to the other, or how much smaller one is compared to the other. And to do that, you always say, twice as big, 3 times as big. We don't say twice degrees bigger. Does that make sense? So that's why the units aren't there. We're talking about how we are kind of amplifying or increasing or enlarging one shape to get the next one. Okay. You're going to see questions that kind of play off of what we should already know for this shape. They want me in this next one to compare angle B to angle D. And now I have to use what we learned in the last chapter. I don't know what angle B is here from the get-go, right? From the onset of the problem. I don't know how big that angle is. Okay, but what kind of shape is this? Any guesses? Any thoughts? What's it look like? Looks like a trapezoid. Now let's ask the question, is it? And trapezoid, you need some parallel lines, right? What do those two angles add up to? 190. Does that make those parallel? No. So those sides would not be parallel. Okay? What do those two angles, 80 and 40, have to add up to make AC and BD parallel? Or they have to add up to 180 as well? And they don't, so they're not parallel. So you have no parallel sides here, right? So the argument, and I don't have a way to find side lengths or measurements for everything, so the only thing I can do is default this thing to a quadrilateral. Okay, even though I drew it like a trapezoid, it's only a quadrilateral. How many degrees are there for the interior angles of a quadrilateral? 360. And so far I used, 230? That plus that should be 230. So that make this 130 degrees. So now if I want to compare those B to D, this third question here, compare angle B to angle D, it'd be 130 over 40. Gives me 13/4. Okay? So what that means to me is that at 13 compared to 4 means that 130 degree angle, if I multiplied it by 4/13, that's the reciprocal, I multiply it by 4/13, it should reduce that down to 40. Does that make sense? Well, if I multiply 40 by 13/4, it will get me to 130. Another way of thinking about it is if you take 13 of the smaller angle, 13 40-degree angles, and you take 4 130-degree angles, and you found those two measurements, 13 of these will be the same number of degrees as 4 of those. That kind of make sense? Okay? So that's the link between what that 13/4 is actually providing us. Okay? The argument, like I said, these are ratios because the units cancel. Okay? If the units would not cancel, you get what we call a rate. Okay? You guys recognize rates on the way to school today. Okay? When you drive to school, how fast do you usually drive? What's the speed limit on one of the roads around here? You guys know? Nobody knows the speed limit? 55? 55, so it's common, 55 miles per hour. What that means is 55 miles compares to 1 hour. Okay? It's not a ratio, and it's not a ratio because we have units left over. Does that make sense? Can you take miles, which is a length, and change that to a unit of time? No. I could take a length and change it to a length, right? I could take miles and change it to feet, miles change to centimeters, miles change to whatever in terms of the length. But I can't take miles and change it to hours, and I can't take hours and change it to miles. So when that happens, you leave the units, and now you get what we call a rate. Make sense? A total per some time usually. Okay. Think about like if you're filling up. Let's look at it this way. Let's go. Like one of the main things that people look at when they buy a car is it's miles per gallon of gas. Can you take a length and change it into a gallon? No. Okay, that doesn't make any sense. You can't do that. So we get that rate. 35 miles per gallon is a rate. Anybody have a job? Anybody ever had a job or worked a particular part of a day for money? Can I take money or dollars and change it into hours? Doesn't make sense, right? Taking a monetary amount and changing it to a number of hours makes no sense. Same way, hours can't be changed into money. So what we get is when you work a job, you work for $1 per hour, right? A certain amount of dollars per hour. That's your rate. Does that make sense? Okay. People that make salaries, they're getting a certain amount of money per year, correct? Okay, so it's a rate still. But there are some situations that when we compare things, the units do cancel and we get a ratio. So this is an example of that. Some of these story problems, they introduce things that maybe you guys have never experienced before. You guys know what a bonsai tree is? Anybody ever heard of a bonsai tree? Landon? What do you think it is? Are you thinking that it's like a miniature version of something? Okay. So a bonsai tree, so there's like a part of like horticulture that is dealing with like small trees. Okay. So karate kid. So it's like a lot of bonsai trees you see in like the Japanese type culture. I think it's Japanese. Like with feng shui and stuff like that. You ever heard of that? You live in caves. All right. So what a bonsai tree is a miniature. It's real life. It's living, and basically it grows and they shape it and cut it and that kind of stuff and manicure it and all that kind of stuff. But it's a real life tree, okay? But it's like sits on your desk. All right. Here they're saying this thing right here, this picture is a bonsai tree, but it is a comparison or like a miniature version of a tree that is out in nature. Okay. So we're saying this bonsai tree, when we measure its height, it's 15 inches tall. When we go out and measure the other tree that it's the relative of in nature, that tree is 118 feet tall. Does that make sense? It wants you to write a ratio of the two things. All right. So when I read this, it says, what is the ratio of the height of the bonsai to the senator, which is the tree that's out in nature? I need to make sure that I understand and I read this correctly. It says bonsai to senator. So when I write a ratio here in a little bit, I need to make sure that I write the correct fraction. Does that make sense? The right comparison. Bonsai to senator. Okay? If you write senator to bonsai, you got the right idea. You're using the right comparison of values just in the wrong order. Okay? So that's one error that people make. The next error is that they say, okay, bonsai. How tall is the bonsai tree? Careful. The bonsai is the one over here, so it's 15, and it doesn't say in the description, but it's in the picture. So 15 inches. And then the senator is 118. Okay? Now, what did I just tell you about ratios? What has to happen for us to have a ratio? They have to be the same units. Units need to disappear, and you just get essentially what we call a scale factor eventually, but we have to have units cancel away. The number one wrong answer for this problem, like in Math Excel, is 15 over 118. Okay? Because we neglect the units. And I don't think that's a fault to you guys. I think what has happened is like 5th grade, 6th grade, you guys spend a lot of time, what's the unit? Make sure you write the unit, right? You had teachers that would mark things off if you didn't write the unit, right? And then you get to a point in the next couple years after that they stop worrying about units, and you just worry about the math, okay? And then we get back to a point now where the units is important, okay? I think in high school mathematics and high school sciences, the units and the math with the units is as important, if not more important, than the actual math with the numbers. If I have the right numbers, I have the right values, but the wrong units, the question is wrong, right? Does that make sense? If I'm supposed to get like 31 feet and I get 31 inches, that's wrong. So we got to pay attention to units. But I think the way that we do things sometimes in our algebra courses and stuff like that, we start to neglect units. And we start to get the impression as students that they don't matter. They matter. Okay, so we'll work with this. So what do you want to do? We need to convert these both into the same unit. What would be the easiest? Okay, so you want both in feet. So if I want to get both of them in feet, what do I need to do this 15 inches?
1 inch, 1 foot.
Say again? Where are you getting that from? Okay. So just be careful. So you're getting. So what you're doing, you're going to say 15 inches, and I'm going to write it this way real quick. But you're dividing by 12, right? Yeah. Now, if I multiply by 1/12 the same way, or the same thing happens, but I know that's going to leave me with feet. Now, just be careful. 15 and 12. 12 goes into 15 one time, right? Yeah. So 1. And now, how many inches would you have left over? 3. Out of how many? 3 out of 12. So 3/12. You can leave it as 3/12, but that's 1/4. So I'm going to write it as 0.25. So 1.25 feet. Well, careful. It's already in feet. Does that kind of make sense to everybody? If I do it that way, and so the feet are going to cancel out. So the ratio that they're looking for here is 1.25 over 118. Okay. Now that's provided we changed everything to feet. Let's do this. Let's change everything. I would, and it's just because I like to multiply better than dividing. Can I take this and multiply it by 12 to put it into inches? So I'll have 15 inches on top. When you multiply this by 12, you get that number right there, 1,416 inches. What's going to happen with the inches? Cancel out. Okay. Now the question is, how come the way maybe Skylar let us to do it and the way that I let us to do it, how come they're different, but I'm saying that they're okay, they're both the right answers? Okay, so when we divide those as decimal and put them in and compare them in the same version of numbers, so same format, change them both to decimals, there's what they both turn out to be as decimals. Does that make sense? And I think Desmos does something real nice for us. It will actually take this, okay, which is basically what they're doing is they're moving the decimal place over 2 spots in the top, and they move it over 2 spots in the bottom, and they see what whole numbers they divide by. So it reduces it to that. Is that the same thing that they're doing there? That make sense? Okay. Do you guys know anything about how I would check? Because this is going to kind of lead us into the next concept eventually. How I would check, even if I didn't put them both in the same format, how could I check that 1.25 over 118 is the same thing as 15 over 1416? Is there how you could check that without having to maybe use Desmos or use, say it again? Cross multiply, okay? So just going down to a more simple concept, do we know that 2/3 is equal to 4/6? We know that those two fractions are the same, right? What do we get if I cross multiply there? What's 2 times 6? What's 3 times 4? 12. So because 12 equals 12, that total is 2/3, the same thing as 4/6. Does that make sense? So if we take, let's see here. If we take 1.25 times 1416, gives me that number. Take 118 times 15, you get the same number. So that tells you that those are 2 acceptable versions of the same amount. Okay. Why do we talk about that? We get to a homework question, and they ask us to type an answer in, or we're working with a friend or something like that before we type answers in, and we both come up with different answers, you still both might be right. You just got to compare your numbers. Should be on the lookout for that kind of thing. All right, so this next concept is not extremely prevalent in a lot of things that we do beyond like this section, but there have been questions on the in-course exam that ask about extended ratios, and it's just the ability to compare more than two things. I want to compare 3 things or 4 things or 5 things. We can do that, but we have to use a different type of notation to do it. Okay? So one of the most common things is to say I've got a triangle here with side lengths A, B, and C, and I want to compare side A to side B, but then at the same time I want to compare side A to side C. And then I want to compare C to A and C to B and then B to A and B to C. So there's a lot of relationships here that I might want to compare. The way we do that, if I want to compare 3 things, is that we have to use the colon notation here, because obviously writing 3 things as a fraction doesn't make sense. There's only 2 positions for a fraction, right? Okay, a divisor and a dividend. So we have to use this notation. But basically all it says is that you can take A and compare it to B. So the first 2 things, you compare those together. Obviously, we get that one, right? We can take B and compare it to C. Sorry. B compared to C. And then the last one will be A compared to C. And we get those 3 ratios. Does that make sense? So when they give me an extended ratio of 3 things, A compared to B compared to C, they're actually giving me 3 smaller ratios. Okay? 3 smaller, maybe fractions. We can think about it as this way: A over B, B over C, A over C. Okay? We'll use extended ratios when we start talking about like sine, cosine, tangent, kind of how we develop those things. Will help us, or this extended ratio process will help us prove maybe some of those things. We don't usually, I told this to the last class, and it's just kind of a pain in the butt. We usually don't go like A compared to B compared to C compared to D in this class. We could. We could put as many things here as we want. Okay? But when we do that, we start to increase the number of comparisons that get made kind of exponentially. And what I mean by that, think about this. If I've got A compared to B compared to C, so that means that it's going to break down to something compared to something, right? Before I put anything here, I could put either A here or B or C. Does that make sense? So I could put 3 things in that location in my comparisons, right? Once you put A there, excuse me, once you put A there, you can only put B or C in this box. Does that make sense? We okay with that? Okay. So I get eventually, if I take 3 times 2, 3 times 2, I get 6 total things, 6 total comparisons that can ultimately be made here. Okay. And I've only got this. I've got A compared to B, A compared to C. We can go B compared to C, which I've got. Okay. And we go C compared to A. Okay. And then we can go B compared to A. And what's the next one? C compared to B. There's really a total of 6 things. Does that make sense? But I only wrote 3 of them because, B compared to C and C compared to B, they're just reciprocals of one another, right? So that's kind of why I did that. I only showed those 3. But and those are the 3 that we're going to be most comfortable with using. If I did something like this, I can go A compared to B, but A can also be compared to C. A can also be compared to E. Does that make sense, everybody? When I go B compared to C, B can go to C, but B can go to E, and B can also go to A. And the next one will be C goes to E, C goes to A, C can go to B. And the last one would be that E can be compared to A, E to B, E to C. And I end up with a total of 12 different ratios when I compare 4 things. Does that make sense? And that just gets messy. But the reason is because in the first box, I could put 4 things. I could put either A, B, C, or E. And once I define that I'm using A, then I can only compare A to 3 other things, right? B, C, or E. I don't know why I skipped D. But if I do that, 4 in the first, 3 in the second, 4 times 3 gives me 12, right? You guys remember last year doing, it might not have been last year, it might have been the year before. If Sally has 3 pairs of shoes, 4 pairs of pants, and 5 shirts, how many outfits can she wear? It's 3 times 4 times 5, right? Okay, it's a fundamental counting principle. That's what's going on here to determine I could have 12 things. So, why am I saying that? Because if I do put D in there then, I could have 5 things in the first location, 4 in the second, so now I have 20 things I'd be looking at, right? Just the amount of comparisons get very large very quickly. So for the most part, when we do an extended ratio, we're only going to use 3 things. Okay, and the argument is if we can do it with 3, then we should be able to do it with 4 and 5. It just might take a little bit longer time to do that. So here's the kind of question you see with an extended ratio. Okay, and they're usually not much different than these. They might talk about the perimeter of a triangle or a rectangle or some other shape, but they're very similar to one another. Okay, basically what's going on here is that they say you've got these 3 side lengths that, in comparison to one another, are in this ratio of 4 to 6 to 9. Okay, so when I compare things, it's like comparing. You know, when I said my age, like 4 times my age is equal to 2 times your age, okay, I wouldn't say it that way, right? I would say 2 times my age is 1 times your age, right? Or 1 times my age is twice your age. Something like that. I would reduce is what I'm trying to say, right? Does that make sense? So when they say 4 to 6 to 9, that's the reduced version of how the sides compare to each other. The sides could be 8, 12, 18. Does that make sense? Think about this. It's 8 to 12 to 18. Is that a 4 to 6 to 9 ratio? Do they all divide by 2 and reduce down to 4, 6, 9? Does that make sense? Okay. But now here's the thing. Do they add up to 190, as the perimeter says they should? Is 8 plus 12 plus 18 equal 190? That kind of makes sense? Okay, so these are not the 3 sides. So what if I triple them? What if I go 4 tripled would be 12, 6 tripled is 18, 9 tripled is 27. Do those add up to 190? No, right? So doubling doesn't work, tripling doesn't work, see if quadrupling works, and that's kind of the trial and error type method. Okay? Try to enlarge each one of those by the same amount and see then if their total equals 190. Well, it's a little bit easier maybe to work backwards. Okay? If I know that 469 is the reduced comparison, the reduced ratios, through reduction, if I ask you, just looking at like, let's just say 12 compared to 18, what are you going to divide both those by? 6. I divide that by 6, I get 2. Divide that by 6, I get 3, right? Okay. So reducing is done through division, right? How do I enlarge it? How do I go back from 2/3 to 12/18? Here you divided both by 6, right? So when I multiply by 6? So these are the reduced versions. 4, 6, and 9 are like the 2/3. And I want to unreduce them. So unreducing means they got to multiply, right? Okay. Now here, I knew I need to multiply by 6. Here, I don't know what I'm multiplying. Okay? But when I did multiply by 6, I multiplied both things by 6, right? So here with this 469, I don't know what I need to multiply by, but I know each one of them needs that applied to it. So if you don't know what to multiply by, that multiple is x. It's unknown, right? Does that make sense? Okay. If I take 4x divided by 6x, does that give me 4 over 6? If I take 4x compared to 9x, does that give me 4 ninths? If I take 6x compared to 9x, does it give me 6 compared to 9? And those are the ratios that are seen here with 4 compared to 6 compared to 9. Now they should produce a perimeter. Perimeter means what with these side lengths? How do you find perimeter? Do what with all your side lengths? Add them up. Okay. And what should my side length total? 190? That make sense, everybody? Okay. So what this is going to do is it says, okay, take this 4 and enlarge it by the same amount that you enlarge 6 by. Enlarge that by the same amount that you enlarge 9 by. When that happens, you should get 190. Well, how many x's does that give me? Okay. Gives me 19x equals 190, and you're saying x then is 10. Okay. So x is 10. So 10 is that number that each one of those got reduced by to give me 4, 6, and 9. Does that make sense? So if I'm going to enlarge them, I take 4, multiplied by 10, gives you 40. 6 multiplied by 10 gives you 60. 9 multiplied by 10 gives you 90, right? Your 3 side lengths are 40, 60, 90. Those add to 190? And if I reduce them again, do they get back to 469? Okay, so that's the approach that you're going to use with those types of questions. When they give you an extended ratio, they're going to tell you something that connects or interrelates those ratios, like perimeter does here. It says you're going to add those things together. It might tell you at some point, like area, might be an extended ratio of 4 things. It might be the perimeter of a rectangle, or the perimeter of just some quadrilateral. And you basically just slap an x on each one of these, 4x, 6x, 9x, and then look at the formula that is essentially being told to you so that you know to add the 4x, the 6x, and 9x, and set that in equal to your total. Okay? Most of the questions are going to be very similar to this one, where you're adding these things up with an x on them and setting equal to the total that they provide you. All right, so we talked about this a minute ago. When we have two ratios that are equal, that's called a proportion. Okay? Two ratios that are equal. So 1/2 equals 2/4. 1/2 equals 2/4. That's the kind of go-to example a lot of times, because if I cross multiply, 2 times 2 is 4, 1 times 4 is 4, and we've got our cross products that are being equal. Okay? But that's a proportion. When we said 15 compared to 14/16 equals 1.25 compared to 1/18, that's a proportion. Those two values are the same thing. Those two fractions represent the exact same amount. Okay. In order to check proportions, okay, we can do the whole, change them both to the same format. Okay. So maybe, if I were to look at this one here, one of the procedures would be, 15 over 14/16 is equal to, now changing to the same format, I would probably want to move that decimal place 2 spots, so 125, and then do the same thing on the bottom. Okay, and now I would just go through, those aren't now, they're better now because I don't have a decimal, right, in the numerator, but they're really not the same format because they're both unreduced. Does that make sense? So if I go through and reduce both of those, I think we got down to like 5 over 472 or something. Yeah, we could reduce both those to 5 over 472, and you're going to see then that they're equal, right? And that takes some time and effort. That takes some algorithms that I have to understand on how to take that decimal of 1.25 over 118 and change that to a fraction without a decimal. Okay? The quick way of checking to see if two things are creating a proportion is to do what Skylar told us and to cross multiply. Take that number times that one, okay, and then see if 15 times 118 gives you the same product, okay. In general, this is how they write it, okay. They say if you have A over B equals C over D, and at the beginning they tell you that C and A can be any number they want to be, B and D can be any number they want to be, but the B and D cannot be 0. You cannot divide by 0, right? But what they're saying, if that is a proportion, then A times D will equal the same thing as B times C. Okay? That's the phrase that you've heard in the past, that cross products are equal. Have you heard that phrase before? Cross products are equal? Okay? And that's how you solve a proportion. That's, when I give equations that have fractions in them, that's the number one place that people want to go to, is just start cross multiplying, because that's what they remember the most, I think. Okay, but you can only start cross multiplying if you have two fractions that are equal. Okay, now this will be the last thing we talk about today. But this is a set of vocabulary words that are really kind of maybe pointless for us, other than the fact that they use them quite a bit beyond this. Okay, because we got cross products already as our phrase, and we know that's true, right? Our textbook, higher level textbook, the end of course exam, usually doesn't use the phrase cross products. Okay, cross products is kind of an elementary phrase. Okay, it's more like, when we talk about division, we don't say goes into anymore, right? We say divide. Okay, so cross products is kind of analogous to like that third and fourth grade phrase of goes into. So when we talk about cross products, we want to talk about the two sets of numbers that we actually multiply. Okay? So when I do cross products in a fraction, 2 and 6 are the numbers that get multiplied, right? Okay? Those are referred to as our extremes. Okay? And when you think about things that are extreme, think about temperature. I think that's when you're talking about a scale or the word extreme, talking about scales is the best. So let's think about our temperature scales. Okay? Extreme temperatures would be what? What's an extreme temperature? Okay, -10. Okay? Is -100 more extreme? -1,000 more extreme? So those numbers are further and further to the end of that scale, right? If I have a thermometer, okay, so our normal thermometers probably go to like -40 and up to like 120, right? We don't really need thermometers beyond that, okay? So -40 would be an extreme and 120 would be an extreme, right? Really, really cold or really, really hot. But they're the values that are on the end of our scale, right? When I look at this, would you agree that 2 and 6, if this is a scale, 2 and 6 are at the ends of it? That make sense, everybody? You guys know what bookends are? I don't have any on my bookshelf though. If on my bookshelf, if I had like only like one of those shelves had like half those books, all the books would slide down and fall, right? So they take really heavy objects and put them on the ends, right? And they squish them together, and the books can't move those heavy objects. We call it bookends. Okay. Your extremes are kind of the bookends. They are the starting and ending of your proportion. Okay. The way I remember it when I was in school is the extremes are the first and last thing you say when you read the proportion. 2/3 equals 4/6. 2 was the first word, 6 was the last word, right? So 2 and 6 are my extremes. Everything else then is the means. The means are in the middle. You guys have heard mean, median, modes, right? Those are different values for explaining middle. Okay? Mean is one of those. Mean is referring to the middle or middle statistics. So means the things in the middle. Extremes means the things on the end. Okay? Now, why do we talk about that? Is that when we get through this chapter, there's going to be several other vocabulary words and procedures that use the word mean. Okay, and it's talking about the blue numbers up there and what we have to do with them. Okay, so instead of using cross products, okay, just cross products is just kind of looking at kind of this bubble and that bubble together. Okay, we can break them individually and say, okay, the means is the 3 times the 4. The extremes is the 2 times the 6. Does that make sense? Okay. So just be on the lookout for those words. Last class we got through this question, so we'll start this on Monday. On Monday, all I really want to do is go through example after example after example of how to use ratios, how to use proportions, how to adjust units if needed, situations where maybe we don't need to adjust units because the algebra is going to work out for us in the end anyways. I think if we can understand units, you guys have done like in science, you guys in chemistry? Who's in chemistry? Okay, so you guys have done like unit analysis, right? Like changing, like you've used Avogadro's number and moles and grams and that kind of stuff and how you get units to cancel out. We're going to do a lot of that here, okay? So if you don't understand how to do that or it provided struggle, hopefully I can make it simple for you. But we have to be able to do it with ratios, proportions, and the stuff we do in Chapter 7.